Hello girls, welcome to my dining room table where we're about to go through the exciting world of equilibrium. Couple things before we start, just in terms of what this is. Not going to do anything too complicated. I'm literally just going to go through the notes you've got yourself at home, explain them, highlight any key points, and sort of explain any concepts that we've got within it. You may not need this whole video. I realise depending on what class you're in, you've either done some, if not all, of this topic already, but just thought it'd be worth doing the whole topic as an enclosed video. So it might just be a case you need to fast forward to the bit you need to clarify within your notes, but the whole thing will be here start to finish. And just get straight into it. So the first concept in equilibrium is the idea it's to do with reversible reactions. A reversible reaction is a reaction that can go in both forward and reverse directions. You know that already, and you know that the way you show that is with reversible arrows. So A can go to B and B can go back to A here. A very common reversible process would be changes of state. So water goes into steam, steam goes back into water. But also some chemical reactions are reversible too, in that reactants go to the products and products can go back to reactants. This only really becomes interesting when you look at what we call closed systems. So a closed system is when there's no substances able to get in and out and no energy is able to get in and out. Basically it's all enclosed in one container in one sort of condition. Why this is important is that some reversible reactions you don't actually see reverse. For example, if I just have A going to B and C and this is in like an open container, what's likely to happen, especially if B and C are gases, is that once they're formed, they're just going to go off themselves in different directions and not actually meet each other. In other words, if they're actually leaving the system, you're not going to see the reverse reaction. That's only going to become interesting as a process if you're actually able to see B and C go back together to make A. And you're only able really to do that if you actually enclose them in one system or container. So in this case now, it's all enclosed. If A turns into B plus C, B and C can't really get that far away from each other. So at some point they will actually come back and collide with each other and go back to A. In this instance where you've got that enclosed system or closed system, you'll actually have what's called an equilibrium, more specifically a dynamic equilibrium. Because as the forward reaction takes place, the backward reaction will simultaneously take place, and that means at a certain point those reaction rates will be the same. And the effect of that is that your reactants and products will end up having constant concentrations, or like the same amount of both. But underlying that, they will still be interconverting. So the rate of the forward and reverse reaction will be the same, but that allows the reactants and products to remain constant in terms of their concentrations. This is explained in terms of the definition. So in a dynamic equilibrium, the amounts of each reactant and product remains constant, first point. And the rate of the forward and reverse reactions are the same. So those two things together can be a wee 2-mark definition question in the exam. A little sub-definition here just about different types of equilibrium reaction. If you find ones which everything's in the same physical state, most commonly gases, they'll be called homogeneous. They're by far the most common studied reactions in equilibrium. However, if you've got reactants in different physical states like solids, liquids, gases, aqueous solutions, you would call them a heterogeneous reaction as a contrast there. The first little section about studying equilibrium is about how we can actually analyse the position of the equilibrium. So a little bit of terminology we used here. Again, we'll look back to a simple kind of analysis for an equilibrium, just A going to B. Because each equilibrium reaction or reversible reaction is actually different. They might favour one side over the other. You could have one reaction where the forward reaction is much quicker than the reverse reaction, and that would mean you get lots of B being made. But conversely, you could get another reaction where the reverse reaction is much quicker than the forward reaction, and that means you have much more A than B at equilibrium. It just depends on the reaction. The terminology we would use to describe those two different types of reaction is the location that the equilibrium lies, and we'd say it lies to the left on the reactant side or to the right on the product side. And written down here, if the equilibrium lies to the left, it means little product is formed. In other words, it's mostly reactants. If the equilibrium lies to the right, it means that lots of product is formed. In other words, all the reactants have been used up and turned into products. There is a little bit of a more formal way of showing kind of where the equilibrium lies. And this is something called the equilibrium constant, which, to be fair, is not really something you study that much detail at AS level. They will come back in a bit more detail mathematically at A2 level. But for now, all you need to be able to do is, if they give you a reaction, this one's written A, B, and C, and D, is to convert it into the expression for the equilibrium constant. Essentially, all you need to look at is the reactant side, the product side, and what these are properly called the coefficients, but basically the balancing numbers in front of each of the things on each side. The general trend is, for a Kc expression, it's always going to be a fraction. The top of the fraction will always have the products, and the bottom of the fraction will always have the reactants. You put the products in square brackets because the square brackets are shorthand, or like kind of notation to mean concentration in moles per decimeter cubed. So at the top line we've got C in square brackets multiplied by D in square brackets. What you also notice is the balancing numbers now become the powers, or like the squared, cubed, etc. For each of those terms. So it becomes C in brackets to the power C, D in brackets to the power D. On the bottom you've got the same kind of idea for your reactants. So A to the power A multiplied by B to the power B. Obviously this makes much more sense in terms of a real example. Here's an example here. You get sulfur dioxide reacting with oxygen, forming sulfur trioxide. This is the contact process you look at the end of this topic. Following that same pattern, we put the products on top. So SO3 square brackets, its balancing number is 2, so it becomes squared. On the bottom of this expression, we've got SO2 in square brackets. That is actually a typo. It should be squared as well. Multiplied by O2, which has got no balancing number, so it just becomes the power 1, which means no power needed to be shown there. The last little bit on Kc in terms of calculation is in terms of calculating the units, because depending on the expression of your equation, the units of Kc will be different. Each term in square brackets is a concentration, and concentration generally has the units moles per decimeter cubed. All you have to do to work out the overall units is to keep track of all your moles per decimeter cubed terms within your expression, cancel down any that cancel out, then show what's left over. In this case, you had SO3 in the top squared, so that becomes units wise moles per decimeter cubed squared. On the bottom you've got SO2 squared times by O2, so concentration squared times concentration. That's what you see here. If you cancel that down, the two squared terms will cancel each other out directly just by cancelling fractions, and that will leave you with 1 over mole per decimeter cubed. Obviously, if you've got powers on the bottom of a fraction, you can just flip them over. So that's the same thing as saying moles to the minus 1 decimeters cubed. Now, mathematically speaking, you should probably write this as decimeters cubed moles to the minus 1, because that keeps the powers in order. But in general in chemistry, the convention would be that you always keep the moles first before the decimeter cube bit, even if your powers are kind of flipped like we got there. A little bit of analysis on like your values of your Kc expressions. Again, this is more of an A2 kind of question, but you can get like a very surface level understanding at this point. Even if you look at this one, if this reaction did very much favour the right hand side, in other words the products, that would make the top of this fraction very top heavy. So you have a lot more concentration of chemicals in the top than you do in the bottom. That would give your Kc expression a very large term, much bigger than 1. However, if the equilibrium favoured the left hand side, in other words you've got much more reactants and products, that would make this fraction very bottom heavy, which make it quite small, make it much less than 0. So it's just got that kind of level of understanding you need for the sizes of these Kc terms. A high Kc value, indicated much bigger than 1, would indicate the position of the equilibrium lies to the right hand side. The opposite, a low Kc value, which is less than 1, a bottom heavy fraction, that would indicate the position of equilibrium lies to the left hand side. Just on the back of that, you will have got this done from class already. I'm just going to go through one final example just to do it in front of you. This is what you might have to do in an exam. They give you an expression, you have to convert it into a Kc expression. I'm just going to do C here in front of you. Here's the equation, 2NO plus O2 goes to 2NO2. Kc expression, products on top, in square brackets, NO2. to the power of whatever balancing number they have, so it becomes squared. On the bottom you've got the reactance NO. This one needs to be squared as well, multiplied by O2 in square brackets. If it asks you for the units as well, that could be an extra mark. Again, you substitute moles per decimeter cubed anywhere you've got an expression within your KC expression. So top line will be moles per decimeter cubed squared. Bottom line will be moles per decimeter cubed squared again, moles per decimeter cubed. And you'll see this is actually pretty much the same as the example on the previous page. Those two will cancel each other